Hello and welcome to this EE328 lecture video on discrete time systems and deriving the impulse response given the difference equation. So the impulse response of a discrete time system is a little bit of a misnomer. So we're not talking about Dirac delta as an impulse, but rather simply the signal, which we call d of n, that is 0 for all time, except at time n equals 0. So this is the piecewise defined function. It's 1 when its argument equals 0, and it's 0 forever else. So in some books this is called the unit impulse in discrete time. In some books this is called the unit pulse. In some books it's called the unit sample. Those are all interchangeable terms. I'm going to probably call this the unit impulse because I like to call the response or the output of a system due to this the impulse response. And I like calling it that because it serves the same purpose in discrete time as it did in continuous time. I also want to call your attention to this word in the title of this slide, and that is this is the output due to a relaxed system. So I haven't used this phrase relaxed much before, but what I essentially mean is that there is no energy stored. So no stored energy. Another way to say this is 0 initial conditions. Another way to say this is that the shift register is empty. Okay, so those are all equivalent characterizations of a relaxed discrete time system. So that means that essentially the impulse response is a zero-state response. It's a zero-state response due to a specific input, the unit impulse. Now, we had two classes of discrete time systems. They were non-recursive and recursive. The easier of the two to get the impulse response is a non-recursive filter. So remember the structure. The difference equation for a non-recursive filter has no extra y of n delay terms, and it's comprised exclusively of summed of scaled shifted x of n terms. And so the way to derive the impulse response for this kind of system, up to m shifts on the input, is to simply let the input be the unit impulse, in which case we can go through this kind of n by n, if you like. So for n equals 0, this is the output due to a unit impulse, which we call little h at time 0, is b0 times the impulse at 0 plus b1 times the impulse at -1 plus on and on and on. And I want you to see that all of these are 0 except for d of 0, which is 1, which is why h of 0 is just the first coefficient. So let's turn the crank and try the n equals 1 case. This gives us h of 1 is b0 times the impulse at 1 plus b1 times the impulse at 0 plus b2 times the impulse at -1, and on and on and on. Now this term goes to 0, and the first term goes to 0, but the middle term goes to 1. And so that's why at n equals 1, we only get b1 in the impulse response. And you can continue this exercise for all m plus 1 time instances. And these b's are actually just simply known as the filter coefficients. Okay, they fully characterize a non-recursive filter. Now contrast that with a recursive filter, in which we can and will have sums of shifted and delayed versions of the output. Now I'm going to treat what's called the single input case. But it shouldn't surprise you that if we can get the impulse response for this case, then later we can use linearity and time invariance to perhaps scale this by something and add shifted versions of it as well. But for starters, let's just do x of n here. So the other observation is that the impulse response ought to be a zero-state response, right? Because it's the output due to a relaxed system. So that should tell us h ought to look like a ZSR. which means the first step would be to find the characteristic modes and then check for the forced modes. But what is the forcing function? The forcing function is the unit sample or the unit impulse. And there are no modes associated with this because the only time it does anything is at n equals 0. So there are no forced modes. And I want you to see the conflict between these two statements. The output should be like a ZSR, which means we need a forcing function. The forcing function produces no modes, which means how can we get the ZSR? And so the answer to this is that, yeah, the ZSR contains force modes, but it also contains characteristic modes. And in fact, those are the only modes present in the impulse response. This is the same result we had in continuous time. So even though it's a ZSR, the impulse response is comprised exclusively of characteristic modes. Now, how much of each mode is the next question? What are the coefficients? To establish that, let's plug in x of n equals d of n, and then write out the whole left-hand side. So again, if my input is the unit impulse, then my output gets this symbol, little h. Now this expression has to hold for all little n, including at little n equal to 0. And in this case, we have h of 0 plus a1 h of negative 1 plus a2 h of negative 2 all the way to h of negative capital N. Now at n equals 0, we know d of 0 is 1. Now here is where thinking of the impulse response as a zero state response is important. And that's because it allows us, if we treat it as a ZSR, then all of our initial conditions at negative times have to be 0. This is due to the ZSR nature. Or you can think of this is it due to us assuming that the system was relaxed. Now the one term that doesn't get that assumption is this one. And that's because the right-hand side equals 1, the left-hand side has 1 degree of freedom, and so we must have that little h of 0 is 1. Okay, so yes, the impulse response is a ZSR, but it's a special ZSR in which all of the initial conditions are 0 except the initial condition at 0. We set that equal to 1. So the conclusion from this slide should be that the impulse response as a function of time is going to be comprised of exclusively homogeneous modes, and you solve the quantity of each mode with a set of initial conditions, h0 equals to 1, and all priors set equal to 0. Let's see an example. Okay, so again, first things first is we want to take this complicated right-hand side and replace it with the single input case. So for starters, we are going to ignore the given right-hand side and replace it with a simpler one. Okay, so now we're ready to solve for the impulse response of this simpler system. The first step in finding the impulse response would be to find the characteristic roots. So here we go r squared minus 1/6 r to the 1 minus 1/6 r to the 0, set that equal to 0. This factors into a first characteristic root at positive 1/2 and a second characteristic root at negative 1/3. This also means that the homogeneous response has to be some amount of 1/2 to the n and some other amount of 1/3, negative 1/3 to the n. Okay, so because the impulse response in the single input case, so this sub 0 denotes single input, just to make sure we don't confuse it with the final answer, h0 of n is going to have this exact same form. Okay, so now we use our initial conditions. So at n equals 0, h0 of 0 is 1 by the result from the last slide. And so that is c1 plus c2. We have two unknowns, so we need to go one time step back. And at n equals -1, the initial condition there is 0 from the previous slide's argument. And then the right-hand side simplifies to 2c1 minus 3c2. If I solve this system simultaneously, I get c1 equals 0.6 and c2 equals 0.4. So that tells me that at least in the single input case, the impulse response is comprised of two modes, and it's 6/10 the first mode, 1/2 to the n, and it's 4/10 the second mode, which is -1/3 to the n. Also, the unit impulse comes along at n equals 0, and for a causal system, we must have 0 response before that. So that's why I tack on that unit step at the end. So now we're ready to undo our simplification and try and solve this for the more general right-hand side. So the true impulse response, due to linearity, should be twice the single input response minus 6 times the single input impulse response shifted by 1. Okay, so if you plug in our result, this is going to get a little messy, but it's 1.2 times 1/2 to the n plus 0.8 times -1/3 to the n. Those terms start at n equals 0, and we're going to subtract 3.6 times 1/2 to the n minus 1 plus 2.4 times -1/3 to the n minus 1, and these terms only become active at n equals 1. So this is fine. This is a closed form expression. If I hand you any little n, you can plug it in here and you can calculate h at that n. It's a little cumbersome, and so especially if you were going to try and code this up, it might pay dividends if you tried to simplify it a little further. So what's tricky is that this line is active at times that are different than this line, and the only time that they're not both on is at n equals 0, h of 0, right? This second line is off at n equals 0, so we only get the first line. We get 1.2 times 1/2 to the 0 plus 0.8 times -1/3 to the 0, and that's simply 2. Now for all times greater than 0, so at any time greater than 0, h of n has the following form. It's the first line, 1.2 times 1/2 to the n, minus 3.6 times 1/2 to the n, but I need to knock down one power here, so I'm going to divide by the base. And now let's do the other mode. So plus 0.8 times -1/3 to the n minus 2.4 times -1/3 to the n divide by the base. Okay, so I have repeated h of n for n greater than 0 down here, and I've written it a little funny because I've tried to make all the exponents be the same. And I can do that by borrowing bases and dividing by them. Okay, so if you simplify this line, it actually merges nicely. You get -6 times 1/2 to the n plus 8 times -1/3 to the n. And so this is true for all n greater than or equal to 1. But the cool thing is that at n equals 0, this reduces to -6 plus 8, and it's actually what we want. And so this actually holds for n greater than or equal to 0. So this is a general way to write the impulse response. h of n is negative 6 times 1/2 to the n plus 8 times negative 1/3 to the n. All of that starts at n equals 0. Final answer. So now that we have, and I want you to see that this is a little bit easier to write. So in particular, it's easier to type into MATLAB. This is the result of that function. This is negative 6 times 1/2 to the n plus 8 times negative 1/3 to the n times u of n. So starting at time equals 0. Okay, so this is a summary of what we just showed, is that when the unit impulse signal comes in to the system described by this linear constant coefficient ordinary difference equation, the output, which we call the impulse response, looks like this. It starts positive, then it dips away negative, and then it kind of settles out. Now, what's important to conclude from this? Well, there are a couple of important things. So firstly, we are going to use impulse responses in the same way that we use them in continuous time systems. But in particular, I think it's a little bit easier to see why we can compose any input out of unit pulses. So, for example, if I wanted to now ask you, what's the output of the system when the input is a pair of pulses, or a triple of pulses, or 3 pulses and then a larger pulse? Well, doesn't linearity tell me that it'll be h of n from that one? It'll be h of n minus 1 from that one. It'll be h of n minus 2 from that one. And it'll be the magnitude of this, say 2, times h of n minus 3 from that one. And so I hope you see that in this way, I can construct any discrete time input by knowing the magnitudes of these samples, and they get lined up out here in front of the h's, and then the delay term as well. So what we've done, we've actually written our very first convolution. We don't know that that's what it is yet, but that is where this is heading, discrete time convolution. The other important thing to recognize here is that the presence of a positive characteristic root didn't make the impulse response blow up. So remember, R1 was 1/2 and R2 was negative 1/3. And so this gets back at what I was saying the other lecture, is that in discrete time, it's not whether your characteristic roots are in the left half plane or in the right half plane. It is more, the stability of the system is dictated by the modulus, or the magnitude of the roots. And so both of these roots, if you plot them on the complex plane, if this is the unit circle, R1 is right here, and R2 is right here. And so even though R1 is positive, we get an impulse response that decays. And that's because we're raising R1 and R2 to progressively larger integer powers. And if I have a fraction that I raise to progressively larger powers, the result gets smaller and smaller. Okay. So this is another indication that stability in discrete time systems is still controlled by the poles, is still controlled by the characteristic roots of the characteristic polynomial, but no longer is the real part negative or positive. Now it is the complex magnitude greater than 1 or smaller than 1. Okay, more on that in the coming lectures. Thank you.